Hello everybody, welcome back. This is lesson 3 in unit 11. Today's topic, we're going to be talking about what half reactions are and how to write them. So the best way to go about this is to follow along with the note sheet and follow with this video. Now it doesn't look like there's any homework due tonight. Just make sure that you are following the calendar and schedule posted on the website and whatever other instructions your teacher gives you. So a quick recap from yesterday. We were talking about is something redox or not. And a quick tip that we had shared was it is redox if it's a single replacement reaction. And essentially anytime you have an element all by itself and then it's not by itself later on. It is not redox if you are a double replacement reaction. So using this logic, either a single replacement or some kind of solo element. So technically we can even fit in synthesis as that because you're starting with two small things, depending on the synthesis reaction and depending on the decomposition reaction, they can also be redox reactions. So for the first one, we have O and H by itself. This is a very simple decomp reaction. So if you have things by itself and then they're not by themselves somewhere else in the equation, this is a redox reaction. For number 2, you have oxygen all by itself in the beginning and it is not by itself at the end. So that means it did change, so that makes it a redox reaction. And lastly, for number 3, this is a prime example of a double replacement. It's also a very, very simple neutralization reaction. This is not redox. If you don't believe me for any of these equations, you can kind of use that same kind of box method we used yesterday and track the oxidation number for each element. So the top of your sheet has instead of those 3 questions, a short reading on how to determine if something is or is not redox. Do that. This was kind of walking you through what you would have written down anyway. So when we're talking about half reactions, or even if you take a step back, redox reactions. Redox is talking about oxidation and reduction. Those are 2 separate things, but they act at the same time and together to form these redox reactions. So if we only wanted to look at oxidation or only wanted to look at reduction, that is what these half reactions are, only looking at half of the picture. So again, we're tracking these electrons and you're able to see how they are changed throughout. So if we're talking about a reduction reaction, and so this will be on almost every single PowerPoint. Leo says Gert. So if we're talking about a reduction, that means electrons are being gained. So remember, electrons are negative. If you're gaining all this negative stuff, your overall charge at oxidation number will decrease or reduce. Again, if you're gaining these electrons, they're going to be written as a reactant on the left side of the reaction. Now, the reason we have 3 electrons here is because we have a positive 3 iron ion there, and then an iron atom on the other side. You have to have conservation of charge. You can't just, get rid of charge because you feel like it. So in order to get from positive 3 to 0, you need that 3 electrons. Now reduction half reactions will always have electrons on the left-hand side. Oppositely speaking is oxidation. And again, here comes Leo says Ger. But now we're only talking about Leo. And so if you're losing electrons, anything you lose, if you lose heat, you lose electrons, they are written as a product, like they are there. And that is oxidation. So we can say that the oxidation number goes up. And again, we have this 3 electrons because you have to keep the same charges balanced. So a good rule of thumb, if you have a 0 and then a charge, whatever that charge is the number of electrons that you need to use. So a quick tip is that you're always adding electrons to the more positive side. So oxidation always has electrons on the right-hand side. Reduction always has them on the left-hand side. But if that kind of confuses you, you always add electrons to the most positive side. So if we look at this example, what's more positive, 0 or positive 3? I hope you all say positive 3. So that's why we added them to the side with the positive 3. Same thing if we go back to the reduction half reaction. You're adding them to the more positive side. So let's just try to place electrons on the correct side for these examples. So you have I2 by itself. That means its oxidation number is 0. And then we have 2I minus. So we went from I0 to I plus to I minus. So what side is more positive, 0 or minus 1? I hope you said 0, because that is the side the electrons are added onto. Okay. Next one. So if we have Cr2 plus and we have Cr3 plus, we want to add electrons to the more positive side. What's more positive, plus 2 or plus 3? I hope you would say plus 3. So the electron gets added to that side. And if we work on the last one, Sr, again, when it's by itself, it's 0. And then we have Sr2 plus. What side is more positive, 0 or plus 2? I hope you say plus 2. And that's where the electrons go. So let's just look at the last one in more detail, because we said that you have to have a conservation of charge. So the charge on both sides need to be the same. So if we look at the left-hand side, we have a charge of 0. So that means the overall charge of the right-hand side also has to be 0. But the way we have it written now is that we have a plus 2 charge and a minus 1 electron. So plus 2 minus 1 is plus 1. So that's not right. So that we have to add, or essentially lose 2 electrons to make it even. So now you have 0 on the left side and 0 on the right side. So from here moving forward, we're going to make sure we are balancing these as well. So like I just said, we have to follow law of conservation of mass, conservation of energy. It doesn't really play a part into this type of reaction here, but it still holds true. And conservation of charge. So with all these 3 things, and the 2 mentioned on the slide, you can't just create matter or energy or charge or get rid of it because you don't feel like dealing with it. It's too complicated. That is why we're balancing reactions and all of this other things. So for mass, you have to have the same number of atoms on each side. And for charge, the net charge. So it doesn't necessarily need to be 0. Just whatever the total charge is on one side needs to be the same as the other side. So when we're setting up half reactions, so here is a chemical reaction, and we want to write half reactions for it. Your first step is to assign oxidation numbers. So I'm just going to go through this really quickly. If this still kind of confuses you, go back to the oxidation number video. So anything by itself is 0. Cl is minus 1, and zinc was going to be positive 2. Chlorine is minus 1, magnesium is positive 2. So those are your oxidation numbers. So if we look at each element, Mg is going from 0 to positive 2. Zn is going from positive 2 to 0. And chlorine is going from negative 1 to negative 1. So chlorine doesn't change at all. Now if we're looking at Mg and Zn, because we have this change, we know a redox reaction has occurred. So the question is, which one's oxidized, which one is reduced? So adding our Leo the Gur question. Okay. So with this, if your magnesium is going from 0 to plus 2, its oxidation number is going up. That is oxidation. And zinc its number is decreasing that is reduction. So we can say magnesium is oxidized because electrons were lost and then oxidation number went up, and zinc was reduced because electrons were gained and the oxidation number decreased. So if we're going to write these half reactions, so let's just put this back here so we know what we're working with. Okay, so the first one we want to write is the reduction half reaction. So that's talking about zinc. So we have zinc plus 2, and we have zinc 0. And again, if you're reduction, that means you are gaining electrons, so the electrons need to be written as a reactant. And then we have to make sure they're balanced, so that's 2 electrons. And that's all you have to do for that half reaction. That is it. For oxidation, we're going from magnesium 0 to magnesium 2 plus. And remember, you always add your electrons to the more positive side. Positive 2 is more positive than 0. Now, so oxidation means you are losing electrons, so if you're losing anything, it's written as a product. And again, you want to make sure you have those 2 electrons to balance out that charge. Now, we have to make sure we're balancing the reactions. So if we quickly just rewrite these. Okay. We see that we are gaining 2 electrons here and losing 2 electrons there. So if you're losing and gaining the same amount of electrons, you're balanced, you don't need to do anything. So with that, if we wanted to write our combined redox reaction, you can combine them. So you write all of your reactants, and then all of your products. The order doesn't matter, whatever makes you happy. Now, you'll notice here that you have 2 electrons as a reactant and 2 electrons as a product. If you have the same exact thing as a reactant and a product, you do not need to add that to your equation. So your simplified, perfect, balanced redox reaction would just be this. That is it. So if you look at it, you have 1 zinc on either side. You have 1 magnesium on either side. On the left side, you have a total of a positive 2 charge. On the right side, you also have a positive 2 charge. So that is it. Looking at this example, we have Li, and that is going from 0 to plus 1. And so that if it's going from 0 to plus 1, that means it is being oxidized. And then calcium is going from plus 2 to 0, and that is reduction. So, start with lithium first. We have lithium 0, and we have lithium plus 1. Now we have to figure out where to add the electrons. Again, if it's being oxidized, you're losing electrons. Can't forget Leo says grr. And electrons will always be written as a product in an oxidation reaction. So having 1 electron there makes sense. That is good. If we move on to the reduction reaction of calcium, we have calcium 2 plus and calcium 0. For reduction, you're always gaining electrons, so that means they will be written as a reactant. Again, you're always adding to the more positive side. And we cannot leave just 1 electron. We have to make sure we have 2 of them, and that is your reduction reaction. Now, at this point, we are not done. because we are losing 1 electron there, but gaining 2 there. That is not okay. So if we think about it, how can we have the lithium reaction give off 2 electrons? So easy fix is multiplying the entire thing by 2. So that goes to each and everything. So now you have 2Li0, and you have 2Li plus 1, and 2 electrons. Now this one you don't need to change at all because now we have matching electrons. So that's Ca2 plus 2 electrons, and Ca0. So our electrons are equal. We're happy. We can even get rid of them now. And so now if you're going to write your combined redox reaction, write all of your reactants. So Li, 2 of those, plus Ca2 plus gives you that. Now if you look at the numbers of each element, you have 2 Li's on both sides. You have 1 Ca on both sides. The overall charge of the left side is plus 2. The overall charge of the right side is plus 2. So that means everything is balanced. We are good to go. Next reaction. Mn is going from 0 to plus 4, which means it is being oxidized. Copper is going from plus 2 to 0. That means it is being reduced. So looking at the oxidation reaction of manganese, if I said magnesium before, oops, we have Mn0, Mn plus 4. Remember, electrons are always a product for oxidation reactions, and you have to make sure you have 4 of those to balance out the charges. For reduction, copper plus 2, copper 0. For reduction reactions, you always have electrons as a reactant. And again, you want to make sure that charge is balanced, so plus 2, so you need 2 electrons. Now those are your half reactions, but they're not balanced yet because you have 4 electrons here and 2 there. That means this entire reduction reaction needs to be multiplied by 2, which gives you 2 of these, plus 4 of those, and 2 of these. Now nothing needs to happen to the oxidation reaction, so we can just rewrite that like this. Now we have 4 electrons being lost, 4 electrons being gained. That is balanced. We can now get rid of those. And for the combined reaction, all of your reactants, then all of your products, Mn0 plus 2 of those gives you 1 of these and 2 of those. And that is it. Okay, 2 more, and we're done. So, with this, again, if you're following the same kind of step-by-step thing, it does make more and more sense as you move forward with this. So Ni is going from 0 to plus 3, which means it is being oxidized. Fe is going from plus 3 to 0, which means it is being reduced. So, oxidation, we have Ni0, Ni plus 3, and you have your 3 electrons as a product. Then, if you have your reduction reaction, you have Fe3 plus your 3 electrons, and your product of that. Remember, electrons are always a product for oxidation reactions, and they're always a reactant for reduction. So here, we have the same number of electrons being gained and lost, so we don't need to balance anything. And just kind of forget they exist. So our combined reaction, blue, is Ni0 plus Fe3 plus gives you Ni3 plus Fe0. So if you look at this, you have one Ni on both sides. You have one Fe on both sides. The total charge of the left side is plus 3. The total charge of the right side is plus 3. And then lastly is this one. Zinc is going from 0 to plus 2, means it's oxidized. Chromium is going from plus 3 to 0. That is being reduced. So, for zinc, our oxidation reaction, it looks like this, with your 2 electrons as your product. And your reduction reaction looks like CR0, like that. Now, major problem, which isn't really a problem, is that we have 2 electrons here and 3 electrons here. So that means both reactions need to be balanced. So if we think about it, what numbers do 2 and 3 have in common? And the answer is 6. So how do you get them to be 6? So if we look at the oxidation reaction, you can times everything by 3, which gives you 3 zinc and 3 of these and 6 electrons. If you multiply this reaction by 2, you get 2 of these plus 6 of those and 2 of these. Now we have 6 electrons here, 6 electrons there. Now that's balanced. We are happy. You can kind of just ignore those for the rest of the question. And if we're writing our combined reaction, we have 3 zinc 0 plus 2 Cr plus 3. And we have this and that. So if we look at it, we have 3 zincs on both sides, which is good. We have 2 Crs on both sides, which is good. The total charge of the left is plus 6, and the total charge of the right is plus 6. Everything is balanced. We are good to go. So that is it for right now. Tomorrow we are going to practice more half reactions. So if you're still a little bit confused, it is okay. And this half reaction writing comes into play kind of for the rest of the unit. So if it doesn't click now, it will click eventually. On that note, have a wonderful day.